Two are better than one. So which methods are the best? Those that use more than one method at the same time. We're going to start by going back to big data, what we learned about big data, and answer the question, are we truly ready for applications with big data? So what have we done so far? And important is, so far, we still have some very important conclusions to make in these last 4 videos. We've talked about big data, the 3 V's, that is large because of complexity. We haven't really worked with big data, but we're going to on the final exam. We've explored complex networks, genus, scale, small world, components, k-nearest neighbors networks. We really haven't worked with big networks. We've explored a variety of classifiers, linear classifiers, decision trees, logistic regression, and some nonlinear classifiers, k-nearest neighbors, which tries to tap into the underlying structure of the data, support vector machines, which use high-dimensional contexts and are linear classifiers, but in high-dimensional embedding contexts, and neural networks, which are universal classifiers. We've avoided regression. Regression is predicting actual values rather than class label. Most importantly, we've looked at 2 very big and closely related ideas. Information and entropy, information gain, for example, used to construct decision trees, and metrics and validation, determining if a classifier makes reliable predictions, as well as an important modeling technique, maximum entropy, which is closely related to maximum likelihood. In particular, suppose we have 2 models that we fit to a data set, a P1, X as our index for a random variable, and then parameters W1 to W sub m, and P2 of index X with parameters theta 1 to theta sub n. And important is the better model is going to be the one that is more likely to produce the data. So in other words, the data was produced by a process according to some true distribution, and the best parameterized model that we could choose is the one that would have been most likely to produce the data that we actually have. We also said that a better model is one that has maximum entropy for what it does not explain. Turns out these 2 are essentially the same, and let's look at that, and in so doing derive a way of comparing models. So likelihood, if we have a variable y associated with some set of outcomes O1 to OM and has a distribution P of y, then we're using y here because we're usually predicting the class of a given observation. And so P of y is a predictive model, a model for predicting the class of an observation. Let y sub I be the variable for the ith trial, and assume the y sub I, capital Y sub I, are independently identically distributed. And C sub capital N of y is a count of the number of times the outcome O sub y occurs in n trials. Now, by independent and identically distributed, we get that the probability that we jointly have capital Y1 takes the value O sub y sub 1, capital Y2 takes the value O sub y sub 2, all the way up to capital Y sub n takes the value O sub y sub n. That's the product of the probabilities because of the independence. Probability of y1 being O sub y1 times probability that y2 is O sub y2, all the way up to the probability that y sub capital N is O sub y sub capital N. And these are all the same distribution, that's the identically distributed, so we get the product of the p's. So P of y1 up to P of y sub n is probability that y1 up to y sub capital N occurs. And we're going to assume that it depends on some parameters, say R1 up to RK. Then what we're looking for is that the data in the real world, we'd like to say that the real world model has parameters and that the data occurred for some value of those parameters. And therefore the product, py1, given the parameters r1 to r sub k, all the way up to py sub n, given the parameters r1 to I sub k, is the likelihood that the data set occurred. And this product is a function of the parameters. And our goal is to find the values of the parameters for which the data set we are given is most likely to occur. So what value of the parameters would imply that the data set we have was most likely to be produced by this model? So some notation, we're going to let capital PR of y1 given boldface r up to PR y sub n semicolon boldface r. That'll just substitute in for our longer py1 with parameters up to py sub n with parameters notation. So the log of the product, probability of y1 given r up to probability y sub capital N given r, is the sum of those individual probability, the sum of the log of those probabilities. Log of the product is the sum of the logs. And we can group these into common occurrences. So the natural log of L, which is the log likelihood, can be grouped into those trials that have outcome O1 all the way up to those trials that have an outcome O sub m. And we have the log of the probabilities for each of those O sub 1 up to O sub m groupings. We can divide by the number of trials to get the entropy, negative entropy of y, and that's the log likelihood over capital N, and that's just 1 over capital N times the occurrences of outcome O1, sum over that log probability y equals O1 given the parameters, up to the same thing for the O sub m. So we have two models that we're interested in this derivation. So first off is the model in which the parameters r sub 1 star up to r sub k star denote the model most likely to produce the data. In other words, we've found the maximum likelihood model, and the values that give it are r1 star up to r sub k star. There's also a true model, an unknown model that actually produced the data. So how well does the maximum likelihood model approximate the true model? So we can actually sum over the occurrences of outcome O sub y, and if we take the negative entropy as 1 over n times y equals 1 to n of the sum of the occurrences of O sub y, the log of the probability y is equal to O sub y given parameters r, then that's actually going to be the sum, y equals 1 to m, of c sub n of y over n, because that sum over the occurrences just counts the number of times that logarithm occurs. So we call that the empirical distribution, c sub n of y over n, denoted by a p tilde sub capital N. And we call this h of the data, the entropy based on the data of the outcome variable y, is the sum over the empirical distribution times the logarithm of p of y semicolon given r1 star up to r sub k star. So that's the data best fit model in the sense of maximum likelihood and also now maximum entropy. And recall that p sub n of y goes to the true distribution as n goes to infinity. And so therefore the entropy of the true distribution, which we don't know, it's what's producing the data out in the real world somewhere, that's just the negative sum of the probability log the probability. But for a very large n, that's approximately negative y equals 1 to m of p sub tilde of the natural log of p true. So what we want to do is we want to look at what is the relationship between the entropy based on the data, in other words the maximum likelihood estimate, and the true entropy of the variable. In particular with the question of how much does an additional variable affect the estimation. So what we do is a little trick. In the logarithm we have p true of y, so we divide by p of y depending on r1, multiply by P of y depending on R1 divided by P of y depending on R1, R2, and all the way out so that we get cancellation. So the last one will be P of y, give it all the way out to R sub k over 1. And we split off that last term, and that's actually the data, the maximum likelihood estimate. And then inside we have a log of products of these ratios. So we have approximately the sum, j equals 1 to k, y equals 1 to m, p sub n of y, of the log of the probability y given one fewer parameter over p of y r1 up to r sub j, plus the actual maximum likelihood data fit. And that first double sum term is a bias. In fact, Hirotugu Akeki in 1971 studied this bias term and introduced what's called the AIC in 1973. If the natural log of L star is the maximum likelihood estimate, then that double sum of the products is actually approximated by k, the number of parameters. And the AIC is 2k minus 2 natural log of L star, the maximum likelihood estimate. The smaller the AIC, the better the model. So given P1 with m parameters and P2 with n parameters, the better model will be the one with a smaller AIC. Let's look at some examples. So let's look at linear plus noise. Suppose we had y equals 2x plus 3 plus Gaussian noise. And the linear model is y equals mx plus b. The quadratic is y equals ax squared plus mx plus b. And the linear is a special case of the quadratic. So therefore, the linear will always be a worse fit than the quadratic. The quadratic will always be better because it has one extra parameter and includes the linear as a special case. Here is the Python code I'm using to generate this example I'm about to show you. So let's look at the results. The linear model, y is 2.068x plus 3.036. That's close to the 2x plus 3. The quadratic model is a lot worse. For one thing, it actually bends because it's quadratic, and the coefficient of x is 2.8, which is relatively far from 2 in the 2x plus 3. However, if we look at the mean squared error and the r squared, the quadratic has less error and a higher correlation, and therefore, based on standard statistical measures, we would say that the quadratic is a better fit. But the AIC for the linear is 2.977, whereas for the quadratic is 3.341. Therefore, the linear is the better model, even though the quadratic is the better fit. And of course, this would be desirable in this example, that we would predict that the linear model is the better model. Let's look at another idea in information theory that we've actually already seen. Information gain, we saw, was the entropy in y minus the entropy of y given x. You can also show that the entropy of y given x is just the entropy of x minus the joint entropy. So therefore, the information gain is the entropy of x plus the entropy of y minus the joint entropy. But that means the information gain is symmetric in x and y. So let's give it a new and more appropriate name. We call it mutual information. And mutual information, I of x semicolon y, is just information gain. But it's got some nice properties. For instance, the mutual information of x and y is always non-negative. The mutual information of x with itself is just the entropy of x. If x and y are independent, then the joint entropy is equal to the sum of the entropies, and therefore the mutual information is 0. And we have all these other equivalent conditions that we can derive. And what we get from this is that mutual information is a measure of dependence. So in summary, mutual information, the AIC, maximum likelihood, maximum entropy, etc., allow the refinement of existing models, allows the comparison of dissimilar models, and allows alternative approaches. And in particular, what this shows us is that models of big data are always being tweaked, pruned, tuned, refined, redesigned, and combined with other models. And that last one is very important.